Class 10s, just pay attention to this. We did this yesterday, remember? The dependence of the angle of deviation on the angle of incidence. We talked about the graph, and then we talked about the minimum deviation. I talked about this diagram also yesterday. This diagram I talked about yesterday. So that is actually the first point. You have the factors affecting the angle of deviation. We talked about the first point over here, right? The angle of incidence. We talked about the angle of incidence, right? This was the entire, and I tell you this graph is also important. This graph is important. These diagrams are important, right? We go on. Now we go on to the next point over here, right? We go on to the next point, dependence of the angle of deviation on the material of the prism. Dependence of the angle of deviation on the material of the prism. We are going to talk about that now. Is that okay? Right, now material of the prism, actually what they mean is the density of the prism, density of the material or the density of the medium. So more the density, okay, more will be the refractive index and more will be the deviation. It is found that for a given angle of incidence, prism with higher refractive index. Now when they say higher refractive index, actually higher refractive index happens due to the density. More the density, more will be the refractive index, and therefore the deviation will be more. Fine. Then dependence of the angle of deviation on the angle of the prism. The angle, now look at this case here. Look at ray A and look at B. Now if this is my prism here, A, B, C, okay, and A, D, E. Now in prism ABC, look at the angle. It has a small angle. Therefore the ray of light goes there and it stays inside the prism for a smaller duration of time. Okay, and because it stays for a smaller duration of time, the effect on the ray is less. Okay, and therefore the deviation is less. The same thing, now look at ray B. It goes in there, and it stays inside the prism for a longer duration of time. For a prism ADE, for the prism ADE, ray B stays inside the prism for a longer duration of time, and because it stays for a longer duration of time, the effect on the ray is more, so the deviation will be more. Got it? And then the third point, depending on the color of light, color or wavelength. Now, the moment they say color or wavelength, it comes to this. We have done this before also. Look at that. When a ray of light is passing through a prism, it splits up into 7 colors. We'll be coming to this later. There's a big chapter on this coming on later. Okay. So violet comes right down and red right on the top. VIBGYOR. Remember that. Now why does that happen? Because different colors of light have different wavelengths. Now this part, as we say, is the visible spectrum, the spectrum that is visible. Beyond this is the invisible spectrum. We'll talk about it when we come to the chapter. Okay, so what happens is this ray of light, when it this is white, when it passes through the prism, it splits up into 7 colors. Why? Because different colors of light have different wavelength and they travel with different speed. Wavelength will affect the speed. Okay, if you look at this visible part of the spectrum, this is your violet, which has a very small wavelength. Can you see that? And look at the red, it has a long wavelength, so it jumps out of the prism very fast. Whereas the violet, it continues to stay inside the prism for a longer time because of the wavelength. Do you follow what I said? And because of that short wavelength, it stays longer inside the prism or inside the material, and therefore it has more effect on it. So it bends more, splitting from red, and accordingly the others come in. Red has a longest wavelength over here among the visible spectrum. This is called the visible spectrum. Red has the longest wavelength. Got it? Okay, so that's it. These are the 4 points. Remember, they are asked for your question. Okay, now we go further. Unit C, the real and apparent depth. Real and apparent depth in the sense the different applications of refraction in day-to-day life. Where do we find this application in day-to-day life? You must have seen that somebody swimming in the swimming pool and all their legs looked as if they are squeezed. Or when you look at the swimming pool from an angle, you find the bottom of the the floor of the swimming pool is higher than what lower than what it looks, and all that things. Okay, different type of effects that we have in day-to-day life. Now, look at that. I'm trying to explain that part over here. Look at this. All right, here it comes. Now, this is the surface of the water, and this is the floor of the swimming pool. So the object is here. The ray of light coming from the object bends away from the normal, goes that side. But what happens? The eye sees in a straight line, and the eye sees the floor here. The image comes over here. Got it? From denser medium, this is denser, to rarer medium. From denser to rarer medium, the ray of light bends away from the normal. But the eyes cannot take the bending of the light, so the eye sees it in a straight line over here. So this is my real depth, RD, and this is the hold on. Okay, do you follow what I said? This is the real depth, RD, and this is the depth actually that we see. We call it AD, apparent depth. Do you follow my point? This is the real depth, and this is the depth that we see. That is not the real depth, that's the apparent depth. You got my point? Okay, fine. So, here we take this triangle over here, ABO, sin I. No, sorry. This is I, angle of incidence. This is angle of refraction. This is I, so this is I. Alternate angles. This is R, so this is R. Corresponding angles. Equal. Okay. So now I go. OBA, triangle OBA, sin I is opposite by hypotenuse. Sin I is AB by OB. AB by OB. Okay. Sin R, taking triangle IBA. Sin R is AB by IB, opposite by hypotenuse. AB by IB. Got it? Now, the ray of light is traveling from medium to air. We say refractive index of air with respect to medium. Refractive index of air with respect to medium is sin I by sin R. Sin I by sin R. Now, divide this. Sin I by sin R, you divide and see what happens. AB and AB cancels, and you get a reciprocal IB by OB. You will get a reciprocal over here. AB and AB will cancel, and it will become IB by OB. Am I clear there? Now, as I said, we don't work with respect to a medium. We have to go to the absolute refractive index. And remember the principle of reversibility of light. Refractive index of medium with respect to A, which is absolute refractive index. Refractive index of medium with respect to A is equal to 1 by the reciprocal, as we say, of refractive index of air with respect to medium. Medium with respect to air is 1 by refractive index of air with respect to medium. That is your principle of reversibility of light. Now this value is, as we have it over here, 1 by IB by OB. So you make a reciprocal, it becomes OB by IB. So refractive index of medium with respect to air is OB by IB. OB by IB. Now what you do is, you bring this B closer to A. Closer, 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 closer. Let the B come and coincide on A. If the B comes and coincides on A, okay, then OB can be written as OA and IB can be written as IA. You follow that? I got my refractive index of the medium with respect to air which is OB by IB. OB by IB. Now what I do is I bring this B closer, closer, closer and let it coincide on A. Okay, so OB will be written as OA, as you have it over here, and IB will be written as IA. So it becomes refractive index of medium with respect to A is AO by IA. AO by IA, that is real depth by apparent depth. Refractive index of a medium with respect to A is real depth AO by IA, real depth by apparent depth. AO is the real depth, IA is the apparent depth. Am I clear over there? You don't have to worry about the thing, no deductions are coming. Okay, I just did it for your sake, but as I said, the relation will be used for some numericals. It can be used for some numericals. Is it clear? Okay, we have some examples over here, that's fine, you go through it, and then we have the apparent bending of a stick underwater. Now this diagram has come. Now and again this diagram has come. Very simple. What happens is when you put you can see that at home also, when you put your spoon in a glass of water, it looks as if it is bending. Why? Now this is the actual stick here. So we are looking at this point P, OP. We are actually looking at XOP, XOP. Now what happens to OP? The OP goes to OP dash. How? This P, the ray of light coming from here, goes up, bends away from the normal, bends away from the normal, but when the eye sees in a straight line here, P dash. So instead of seeing XOP, we see XOP dash. Instead of seeing XOP, we see XOP dash, which gives you the illusion of bending of light. It's an illusion, optical illusion, right? Because the point P, okay, the ray of light traveling from here bends out away from the normal, produce backward, they meet at P dash, right? So instead of seeing XOP, we see XOP dash, the bending of light. Is that okay? Right, some consequences of refraction. Look at that, stars appears twinkling in the sky. Why? We see the stars twinkling. Then the sun is seen few minutes before it rises. You can get the glow of the sun, okay, in the horizon. Even before you see the sun, you can get the glow of the sun. That's because of refraction. Coin kept in a vessel and not visible from a certain angle. Okay, so when you pour water in it, it becomes visible, right? Printed prints appear to be raised. Okay, if you put a glass block on top of a print, you can see it is being raised. All that is for because of refraction. Pieces of paper stuck at the bottom of a glass block appears to be raised. Same thing like printing. Then tank appears shallow. We have talked about that. Person's leg appears to be short when standing in a tank. Same reason, and so on. Go through all these things. Okay. Might be in class I can draw the diagrams for all these things, and some of them I can explain it to you through diagrams. Okay, right, that is that. Now we go on to a very important part of light. What we say is critical angle, total internal reflection and critical angle. Okay, okay, now look at this one over here. Okay, a very important part of light, very important part of light. Okay, critical angle and total internal reflection. Suppose I tell you the ray of light is traveling from glass to air, rarer to denser, denser to rarer. This will be denser, this will be rarer. Okay, now look at the ray AO, right, bends away from the normal A dash. So A dash, fine. Ray of light going from denser to rarer will bend away from the normal. Okay, so this is my angle of incidence, this is my angle of refraction. I'll call it R1 and I1. Now what I do is I increase the angle of incidence. So you get another angle over here, I2. Okay, increase the angle of incidence. When you increase the angle of incidence, the angle of refraction also increases. You get R2. Okay, now keep on increasing the angle of incidence. Okay, the angle will keep on coming down, the angle of refraction will keep on dipping down, because we know that the ray of light will bend away from the normal. As I keep on increasing the angle of incidence, you follow what I said? As I keep on increasing the angle of incidence, there, the angle of refraction keeps on coming down. Not down, sorry, I would say it keeps on increasing. The refracted ray keeps on coming down. Got my point? Right? And the angle of refraction keeps on increasing. So it goes on increasing. As you keep on increasing the angle of incidence, the angle of refraction keeps on increasing. Finally, it comes to a point when the angle of refraction is 90 degree there. It goes C dash. It was bending, away from the normal, away from the normal, away from the normal, and finally it comes to OC dash. That means the angle of refraction is 90. This angle of incidence is called the critical angle. The angle of incidence when the ray of light traveling from a denser to a rarer medium, okay, the angle of refraction is 90, which gives you an angle of refraction 90. That angle of incidence is called the critical angle. Critical angle of incidence rather. Okay. The angle of incidence, when the angle of refraction, the ray of light has to travel. Now these are the conditions, mind you. The conditions are the ray of light must travel from a denser medium to a rarer medium. The ray of light must travel from a denser medium to a rarer medium. Okay. And the angle of refraction will be 90. That angle of incidence is called the critical angle of incidence. Did you get that, everybody? Is that okay? Say something. Got my point? Fine. So these are the conditions for a critical angle. The ray of light must travel from a denser to a rarer medium, and the angle of refraction should be 19. The corresponding angle to that angle of incidence is called the critical angle. Now, look at that. The ray of light is traveling from glass to air. So we write refractive index of air with respect to glass is sin I, or rather IC, by sin R. Is that okay? Now, so this is refractive index of air with respect to glass is sin IC. Now sin R over here, sin R is what? 90 degree. Okay. Now sin 90 is 1. So this becomes sin IC, critical angle of incidence, by 1. Did you get that? Now we cannot work with this. We have to go to, what is that? Absolute refractive index. So critical angle, refractive index of glass with respect to air is 1 by refractive index of air with respect to glass, which is 1 by sin IC. Okay, I am taking a reciprocal. Remember that reversibility of light. So 1 by sin IC is cosec IC. So refractive index of glass with respect to air is equal to cosec IC, not I only. Okay, this is what the deduction shows. Refractive index of air, ray of light is traveling from glass to air. Here, the ray of light is traveling from glass to air. We say refractive index of air with respect to glass is sin IC by sin R. Sin R is 90 here. So sin IC by sin 90, sin 90 is 1, which is equal to sin IC. I'm using the reversibility over here. Refractive index of glass with respect to air, because this is the absolute refractive index. Whenever I mention the refractive index of any medium, it should always be respect to glass. So which is equal to 1 by refractive index of air with respect to glass, which is 1 by sin, this is sin IC, 1 by sin IC. Yeah, refractive index of air with respect to glass is sin IC, so 1 by sin IC, which becomes cosec IC. That's trigonometry. Am I clear over there, everybody? Fine, I think we need to stop now. It's already 20 minutes. Okay. And sorry, I forgot to tell you one thing. What happens when I go beyond this critical angle? When I go beyond this critical angle, should I finish that? When I go beyond this critical angle, we don't have refraction anymore. We have total internal reflection, TR. When I go beyond this, you follow my point? When I go beyond the critical angle, till the critical angle, there is refraction and the refraction is 90. But what happens when I go beyond the critical angle? When I go beyond this is the one here, I get total internal reflection, no more refraction. Beyond the critical angle, okay, it is total internal reflection. So what are the conditions for total internal reflection? The ray of light must travel from denser medium to a rarer medium, and the angle of incidence should be greater than the critical angle. Angle of incidence should be greater than the critical angle. Angle of incidence should be greater than the critical angle of incidence. Only then there is total internal reflection. The ray of light must travel from denser to rarer medium, and the angle of incidence must be greater than the critical angle. Fine. So remember that, total internal reflection. Is that okay? We stop over there. Fine. Thank you. Okay. Happy holidays once more.